Yeah. And let's start off. Has been another busy day with your seniors results is out yesterday. Means I think we have two people who got 1300 rank, and then we got 2000, 3000, 4000. So hey, we have different stuff. Uh, but I think like I keep saying, it's very difficult to improve in the second attempt. Most people who got the result right, it is all based on your first attempt scores only. Uh, and this is something I have been noticing from last 4 5 years. For example, if you score 150, right, and if you, let's say, you got 98 percentile in mains 1, to get the same 98 percentile in mains 2, you need to score at least 165. 15 to 20 marks, it is bumping up. It actually becomes more difficult. So one of your seniors, she scored 99.26 percentile, and this thing gave a rank of 11,340. So that's what I keep telling you. 99 percentile looks good number, but 1 percentile is almost 12 to 13,000 ranks, isn't it? If 12 lakh people are writing the exam, 1% is 12,000, right? So 99 सुनने में अच्छा लगता है, but end of the day it is that the guy who got 1300 rank, he got 99.82. There is one guy who got 99.82. His rank was 2,400 plus or minus 100. So these are the kind of numbers we're looking. But if you look at the scores, right, the person who scored 99.26, I think this was a score of 183 or something in mains 1. So this is what I keep saying. 60% is what you're looking at. Like if you can maintain that 60, I think this person must have scored something like, maybe a 210 or something, a difference of 20 to 30 marks. 20 marks is 4 questions, isn't it? 5 questions. So that much difference it makes. Anyway, so your seniors thing is going on. Another, I think, 20 days. I'll get free. Then I will run behind you guys. Right. So we'll see. Anyway, let's go ahead with this. Others do keep your cams on. So let's see. The last thing that we did was the self energy part. Perfect. Okay, we did this thing, drop scar question also. Okay, let's do something easy and then we will bump it up. So we have a hemisphere. Right, so plus Q. It's a charged hollow hemisphere. This would be a good mains level question. You have taken a point A, so the C is your center. So forget about the center. You have taken a random point A somewhere here, right? And the question is, what is the direction of the field at point A? So options would be like this. So this is arrow 1, arrow 2, arrow 3, arrow 4, arrow 5. So there are 5 arrows. You have to choose the arrow. In which direction will be the field at point A? So A is a point on the disk, that plane there. So which of the following vectors represents gives the direction of the electric field at A? Which of the following vectors? Arrow 1, arrow 2, arrow 3, arrow 4, arrow 5. Okay. मेरे आर्यन. Right, Samyak. Okay, Shman. What do you guys think? How do we figure it out? Okay, we found this field also great. नहीं Manchika. नहीं Trishi. There is no symmetry there. Thank God. It's not the center. He is somewhere to the left side of the center. So there's no symmetry technically there. So listen, this is what I would suggest. Consider two hemispheres. Let's take this one and let's take one more identical hemisphere. So if you say this is point A, now I don't know the direction of the field. So I will suggest let the field be Ex. So there will be two components, isn't it? Ey. Since we don't know the field, let the field be has two components, Ex and Ey. By symmetry, if you look at this point, can I also argue this also should have Ey and Ex in this way? You agree with this? Now, if you combine them, if you add these two, you will get one full sphere. And now look at the point take a field. Ey will cancel. Now you'll get a field of 2 times Ex. But what is the field inside a hollow shell? Zero. There is no field inside of the hollow shell. Therefore, Ex is zero. That means there is no horizontal component. Field inside hollow shell is zero. Therefore, Ex is zero. That means the field has to be in the direction of Ey. So now you can't calculate this value, but you can tell this much. All these points, everywhere on this surface, the field is acting in the downward direction. It doesn't matter which point you take. At all the points, the field is just perpendicular to the disk. The magnitude we don't know, but we can be sure about the direction. Is that clear, everyone? Magnitude will change. It depends on the value. You have to integrate and do that. Can be done, but again, it's more of a max problem than physics. Clear with this? Yeah, it's a good one. If you see, it is not really that tough. It's a little more, logical, right, Ishman? So yeah, this is the concept there. So we have to use that and finish it off. So the field will be, everywhere so perpendicular to the surface. Clear with this? The next one. This is an important one. Let's talk about pressures. If you take a hollow shell, and if you distribute charge on the surface, sigma. Now think about this. Every positive charge on the shell is repelling every other positive charge. That means every charge is trying to push each other away, isn't it? So the whole shell is trying to expand. Agreed with this? The whole shell is under a constant state of repulsion. The whole shell is trying to expand. So if everyone is pushing everywhere on the surface, so this will generate a pressure on the surface. This is called electrostatic field pressure. Find the pressure on the surface of the shell due to the repulsion among the, its own charges. So this pressure is called electrostatic pressure. This is the full name, electrostatic field pressure. Just call it field pressure. Since all are like charges, the charges will repel themselves. So the shell is trying to expand. Imagine if there is no bonds between them. The moment you keep the shell, it will explode and it'll, all the pieces will fly out to infinity. That means they're all staying together because of the internal forces. So there is a pressure on the surface. These ideas are important. In physics, you will get total 5 different pressures. Fluid pressure, we studied already. This is the second one you're encountering, electrostatic pressure. Next, you'll encounter gravitational pressure. Then you'll encounter magnetic pressure. Then you'll encounter something called radiation pressure. That comes in modern physics. And the best part about these pressures, right? You can use everything you studied in fluid mechanics, the projected area, all that stuff, because Max does not understand which pressure is what. The ideas will look identical. Now, how do we approach this? Think for a minute. This is a little weird, so yeah, we should see that. This itself would be a good question. You know how they can ask you if this was an advanced question. I will say the shell car radius is r, the thickness of the shell is t, The radius is much, much greater than T. B is the breaking stress. Find the maximum value of sigma so that the shell does not explode or shell does not crack. This becomes an elasticity equation. Find max sigma so that the shell does not crack. Means if you keep putting more and more and more charge at one point, the shell will have so much pressure, the shell will literally explode and break into pieces. Now you might think like, oh, this is looking weird. No, you have done this. You have done this in elasticity. ये equation याद है? We have a shell filled with gas inside and you're increasing the pressure inside. Find the maximum pressure inside so that the shell explodes. Exact same question, बस इतना ही difference था. In place of this P gas, now we will put electrostatic pressure. And everything looks identical. You're getting how things are getting connected. So, how do you find the pressure here? So listen, this is a little weird. Like, if you should have seen this once before. But the result is important. So remember this and remember the derivation also, because derivation, there is a small thing there. We're going to use that later in magnetism also. Now, when you take this whole shell, consider a point just outside the surface and a point just inside the surface. Consider A and B just inside and outside the, I mean, they're very close to the surface. Just inside and just outside the surface. Now what we will do, we can write this thing as, take this shell with a small gap. So we will make a small gap here. So the small cavity. I'm just exaggerating it. Plus that small piece. So if you put that piece back, you'll get a full shell. Making sense? Why am I taking a small piece? Remember, you want to find the pressure, isn't it? So I need to take a small surface so that we can find the pressure there. And now remember, A is just outside, B is just inside, A is just outside, and B is just inside. Now, due to this, all this remaining shell, all these guys here, they will be generating some kind of field. I don't know how much. Let that field be E1. And that the field also will be E1 here. Both will be in the same direction. Why? Think about this. For this charge, B and A will look identical, isn't it? Since A and B are so close, every charge here will think A and B are the same point. So whatever is the field at B, you'll get the same field at A.
Sir, but like inside the hollow shell, there's no field, right?
वो cavity है, अभी hollow shell नहीं है वो. You made a hole there. You made a
Okay.
hole. It's not a full hollow shell anymore. Clear?
Yes, sir.
Everyone is clear? So this is a hole there. मतलब, this is a hole. Since you made a hole, it is not a full shell anymore. So it won't be zero. हाँ, अगर वो hole को हमने ये patch से close कर लिया, now it will become zero. Are you getting it? So E1 is the field due to all these guys. Similarly, due to this small sheet, E2 is the field due to this small sheet. This will be opposite here. Why? Because if this is positive charge, the field will be away from the point charge. So E1 is the field due to the shell with the cavity or with the hole. This is not the field due to the full shell. E2 is the field due to that small piece, the hole which you made actually. And you'll understand why I'm doing all this. But so far, the story is clear. Is the story so far clear? We took a shell, we made a hole, we took out a small piece, and then you're saying all that thing is the field due to the remaining shell, and E2 is the field due to the small piece. And now we will say field at A is nothing but E1 plus E2, right? Which is nothing but the field outside. How much is this thing here? So field inside is 0, and the field on the surface is kq by r square. So q by 4 pi epsilon r square. And q by 4 pi r square is nothing but sigma. So this is actually sigma by epsilon. So E1 plus E2 is sigma by epsilon. Whereas the field at B will be E1 minus E2, which is 0. So when I see this thing, clearly we get E1 is equal to E2 is equal to sigma by 2 epsilon. Meaning, look at the situation here. This whole shell is creating sigma by 2 epsilon, and this one chota piece is also creating sigma by 2 epsilon. And when you combine these two, you're getting total 0. Is that making sense, everyone? You might think like, how can such a big thing create the field equal to this? Uh, that is because, even though it looks big, the problem is all these people are fighting, isn't it? This guy is pushing this way, this guy is pushing this way. You're only taking the components, isn't it? They're all not exactly adding up. They're actually fighting. As you get closer and closer, you can clearly see the components are actually getting lesser and lesser. So even though you're big, end of the day, the net effect matters. So what did we prove here exactly? So we found the field due to this thing. Yeah. All clear with this thing? Now, why did I do all this story here? First thing, what are we trying to find? We are trying to find the force on the surface. What is the force on a charge? The force on a charge, listen to this thing. The force on a charge is charge into field. Isn't that the formula we write? Now, what is this field exactly? This is the field due to the remaining charges on small q, isn't it? That E is the field due to the remaining charges on small q. Now, अगर मैंने directly ये formula use कर लिया, if I had used this formula, E is equal to sigma by epsilon, and I can't say this thing, I can't say force on this piece is q into sigma by epsilon. Why? Because this sigma epsilon also contains the field due to yourself. You cannot have the field due to yourself acting on you. Is that making sense? So we needed to find the field on the remaining charges on that small piece there. So now coming back to that, so when you took this small piece here, so on this small piece, the charge is dq, which is sigma into dA. This is the field E. This is the field due to the remaining charges on this small piece. So that is the force I want to find. Remaining charges on the small piece. And we did all that story to prove it is actually half of the total field sigma by 2 epsilon. Therefore, the force on the small piece will be dq into E, which is dq is sigma into dA, and E is sigma by 2 epsilon. If you don't take the 2 and if you write sigma by epsilon, you'll get an answer में 2 का difference, and that option will be there. And if you take force by dA, this becomes sigma square by 2 epsilon. Force by area is nothing but pressure. This is called electrostatic field pressure. Clear with this? So all the story is to find the field of the remaining charges on that small piece. Yeah.
So this field pressure will always act on charges or anything.
Field pressure will act because of electric field. So why will it act on anything? Why will it act on you? You are a
Like I
charge,
mean,
क्या?
no sir, like I didn't quite get the feel कि वो actually है क्या.
क्या है क्या? Simple. Positive, 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 positive. Everyone is repelling everyone else.
So like that
Why
gas.
should they stay here? Why should they stay here? If it is
Oh,
staying
right.
there means there is some kind of force, right? इसको tension वो सब generate कर रहे हैं ना वहीं पे surface पे.
It's like वो gas अंदर भरा है and it's trying
Yeah,
to come
exactly
out.
same. मतलब वो charge को difference नहीं पता चलेगा whether it is due to the charges or due to the gas.
Okay.
It gives you the same feel there. Are you clear with this? So there, you should definitely remember this result. I'll put it down here. This is called electrostatic field pressure. Remember, this will derived for a hollow shell. Huh? Don't use this for any random shape. If I give you cylinder or something, that would change. Sigma square by 2 epsilon. And later on, I'll show you for Gauss law. Like for conductors, this will always work. But ठीक है. Is everyone clear with the proof? So once you got the field, it is done. You will simply say the field on that small piece into charge will give you force, and force by area is pressure. How did we get sigma by 2 epsilon? अभी प्रूव किया ना यहाँ पे E1 is equal to E2 is equal to sigma by 2 epsilon. Right, Trishi? What is E1? So basically this value is E1, isn't it? At this surface, what is the field? E1. At that surface, what is there? dq. Understand? Understood, na, Rishi? Basically, A hai, see, it is like this thing. If I ask you find the force on the small piece, will you say this charge dq into E2 and E1? Which one will you say? You should take E1, right? You cannot find the force on yourself due to your own field. So whenever at F is equal to QE, that E is the field due to the remaining guys on you. Convinced? Still confused? Let me know. But all clear with this thing. Now, what about the second question? Now you can play the second question. It is the same thing. Now you can bring electrostatics, every damn thing in this. So we will take a half shell. So on this, the force will be the pressure, which is sigma square by 2 epsilon into pi r square, the projected area. That's what I'm saying. The max does not know the pressure is coming due to whom. It is a gas or something. It looks the same. And where is this pressure acting? This tension is acting on this surface here, cross section. So the tension is acting on this circumference here. So we get tension is equal to sigma square by 2 epsilon pi r square. Breaking stress B, stress is nothing but tension by area. Which area? The area where the stress is acting, which is 2 pi r into T. And this value must be less than equal to B so that the shell doesn't explode. यहाँ से sigma आ जाएगा. Are you clear with this? So all this will get sigma less than equal to something. That's your answer. The question is become electrostatics. All clear with this? Clear, na, Devanshi? Ovia? Clear with this? Tanisha? Tanishka? Clear? Sudiksha? Sudiksha? Clear? Shayan? Satyasha? Got this? Let me ask you one more like this. Another variation of this. Suppose if you have a soap bubble, S is the surface tension. R is the radius. Outside the pressure is P naught. Someone sprinkled some charge on the surface. Let's say plus Q. Find the pressure inside the soap bubble. Remember excess pressure? That one. What will you write? The pressure inside. This will be a good mains question. Hmm. Hey, it's a uniform charge rate. Don't mess up the question. It's a uniform charge distribution. तो मेंस में इतना क्वेश्चंस पूछोगे ना, you will get confused. Pressure, hey, it will be uniform. Now, why won't it be uniform? How to do this thing? I mean, you can just see and tell the answer. Think of it like this. Generally, what is the pressure ka formula? P inside. P inside will be the atmosphere pressure P naught plus 4s by R. Now you tell me, when this is, all are positive charges, they will trying to repel out. So the shell is trying to expand. Will the pressure be more or less? It should decrease, right? If the shell is trying to expand, it's trying to push opposite to this thing. So this will be minus sigma square by 2 epsilon. Is that making sense? If you go back to the derivation of excess pressure, कैसा गया था हमने excess pressure का derivation देख? Excess pressure in a soap bubble, and we did that derivation. Here, look at the derivation what we did. When you took the FBD of the half drop, we said this is pressure inside into area, this is surface tension, and this is P naught, which is pushing from outside. Now here, the electrostatic pressure will be outside, isn't it? Sigma square by 2 epsilon pi r square. So that is subtracting the pressure, na? Means if you put more and more charge, the pressure inside will keep on decreasing. Are you clear with this? And if you want, I'll put down this picture there. So if you put that FBD of half drop here, this is the picture that would look like. So as you put more and more charge, you will get one more term here, sigma square by 2 epsilon pi r square. So the pressure would decrease. Are you clear with this? So they can ask a question like this: how much charge should I keep so that the bubble won't pop? When will the bubble won't pop? If the pressure inside becomes equal to P naught, it will pop, right? If the pressure inside becomes equal to P naught, that means when this term becomes equal to 0, the bubble will pop. Yeah.
सर आई एम क्वाइट कंफ्यूज्ड यार कि प्रेशर जब हम बोल रहे हैं तब किसका है? लाइक एट द
Pressure is
सरफेस
pressure.
होगा ना?
Surface only. This is the pressure
ओके
inside for the gas inside, right?
सर, but like gas won't experience the electrostatic pressure, right?
Gas won't expand. So you're saying when I pump, air into a balloon, the pressure inside will come because of what? The balloon is trying to compress an array.
Okay.
The, the balloon is trying to compress, right? Because of that, the gas is getting compressed.
No, but
Why
like
will the
the
gas
gas
expand?
exert, like जो
See, the electrostatic pressure is on the soap film, and the soap film is trying to compress or expand. Because of that, the gas inside will compress or expand. The gas does not know who is electrostatic force.
okay.
No, this electrostatic repulsion is not happening within the gas, right? It is happening surface level. But all clear with this thing? So you can put this thing like this. Suppose instead of plus q, if you put minus q, then how will the answer change? Instead of plus q, if you put a minus q, how will the answer change? What do you guys think? Right, Arya. What do others think? Right, Samyak. Yeah, most of you got it. It will not change because whether you put plus or minus, they will still repel. Right? Just because you kept a minus, suddenly it won't start attracting. So people think plus the repel karega, minus attract karega. No, minus will still repel. Are you clear with this? Clear with this? So I'm putting all the sequence of questions in this thing. So this is how they can play around with this. So you can ask you questions on elasticity. You can ask this. It's a good concept though. So you can bring all that stuff that you can think of. So this would be a pretty good advanced question. Standard model though, but you should remember that value there. Clear? And let's see one more. Now the same way, if this thing has a pressure, if you take a uniformly charged sphere, this also will have a pressure. Every point in the solid sphere is repelling everyone else. Find the pressure as a function of x inside. This would be a really good advanced paragraph question. Let me put more details here. Find the pressure inside this. Rho is the volume charge density. R is the radius. So x is the distance from here to here. So the charges inside the thing, they repel each other. In gravitation, this is called gravitational pressure. So the charges inside repel each other. Now, because they're repelling, they will try to fly away, but you're not letting them fly away because you have bonds between them. And because of that, you generate pressure inside. You're seeing this for the first time, but these ideas are important. You should definitely go there and redo these questions again because you will find similar ideas later on in magnetism, gravitation, all this stuff. Find pressure at a distance x. So recently I made up a question like this for your seniors advanced car. So that was pretty weird question though. Center x. So here x ka value lies between r to 0. So if this is an advanced paragraph, I'll ask you this is the first question. Second question I'll ask you. Find the force on one hemisphere. So if you cut this hemisphere into two pieces, they both will repel each other. Find the force on one hemisphere due to the another hemisphere. There. This will be the two questions for a paragraph. Let's find the pressure first. Let's see how will you handle that. You know what was the question I asked your seniors? The question was something like this. In the space, right, we have something called nebulae. These are huge clouds of, gas, which has atomic hydrogen. Ever heard about that nebulae? Nebula, ऐसा कुछ तो होगा spelling. So this is where actually stars form. So the question goes like this: because of the gravitation between them, all these hydrogen molecules start forming a clump. As the hydrogen starts getting closer and closer, the mass will increase, and because of which more and more hydrogen will get accumulated. So what you're forming is a gas spear. Now, as these molecules are coming closer and closer, you will have self energy. Remember self energy ka formula? 3kq square by 5r. So where all these particles are coming closer, all this gravitational energy becomes heat. Because of the heat, that gas becomes temperature will increase. Assume this thing behaves like an ideal gas, PV is equal to nRT. Right? And the temperature keeps rising. When the temperature rises, now inside the hydrogen atoms, which are H plus molecule, nucleus, right? They will try to come closer and they will repel off because there is electrostatic repulsion. But if you can bring them to a distance of 10 power minus 15 meters, there is something called a nuclear force, which comes into picture. So, and the kinetic energy of the molecules will be 3 by 2 kT and 3 by 2 kT. So the thermodynamics energy 3 by 2 kT into 2 times should be equal to the electrostatic energy K Q1 Q2 by R. You're getting how the story is going on? We started with gravitation, then we said ideal gas equation, then we said 3 by 2 thermokinetic energy, then we brought electrostatics. So when you have enough temperature, the hydrogen will combine forming a helium and you get a star. Nuclear fusion starts and the whole thing becomes a star. This is actually how a star forms. So the question goes like this. So find the minimum mass of this star or the planet so that star can actually happen. If you don't have enough mass, the temperature will not rise enough. If the temperature doesn't rise enough, hydrogens will not fuse. If they don't fuse, you don't get a helium and you don't get energy. It won't become a star. So that was a story like that. So you can play around. Anyway, that would be a paragraph. Let's see. How do we approach this? Oh, how do we approach this? Let me ask you this thing. At which point the pressure is zero? This is the first thing you should know. Nee, don't get confused between field and pressure. Both are completely two different things. Arya, if let's say someone, if I tie you to two elephants on both the sides and both the elephants pull you with equal force. So you're standing like this. We bring an elephant and we bring an elephant and we tie you to the elephant. And if the elephants pull you with equal force, what is the net force on you? Zero. So therefore, the pressure must be zero. You should be very comfortable and relaxed. Is that what you will say? So yeah, you look bigger than the elephants, but okay. So don't get confused between net force and pressure. You can have net force zero, but you can be under immense pressure. At infinity, why you want to take infinity? Infinity तो कुछ है ही नहीं ना. Sphere तो है इतना छोटा. You know where you have encountered something like this in circular motion. In circular motion, we had a discussion like this. Uh, we did this thing somewhere else also. I'm not remembering. Circular motion तो याद था. हाँ, this guy. Remember, this free ends have zero tension. So basically, if you have something here, you can't have tension here because there's nothing attached here. Same way, if you have a sphere like this, the free end should have zero pressure. There cannot be pressure on the surface because there is nothing there to pull or push. Yeah, the boundary of the sphere should have zero pressure. That's the thing. Okay, let's see how to approach this. Listen carefully. Now, these kind of questions, right? It's difficult to get an idea. Even if you get an idea, I need to give you like 1 to 2 hours or maybe 1 to 2 days. You need to sit and think. So, getting it. So, and even then you might still not figure it out. So, you're trying to learn here. Don't think like, "Arey, ऐसा question में कैसा कर सकता हूँ?" True. So, I'm teaching you right now. You know. So, if you see something similar, you see a variation of this. Now, you'll be able to handle it. Most people think like this. I should get the idea on my own. Boss, it's not going to happen. It's like, you know what? I can't just put you in an empty space and I ask you to think. To think, you need information. Tomorrow, if you become an architect, you know what they will do first thing? They will take the top 100 buildings and they'll tell you to study each and every building in and out. Literally, ratta मारने के लिए बोलते हैं वो लोग. 100 buildings. Now, when you do that, 100 buildings, right, you actually know every idea. Why is the construction in this way? What is that? What is this? The reason why they tell you to remember all that 100 models is because tomorrow when you do a building construction and you encounter a problem, you can take out a solution from that 100 buildings. Ka some problem must have occurred, something similar. You can take a solution from there and try to replicate it. Clear? So you need to have a certain models with you in order to, encounter a problem. You cannot think in vacuum. Think of like this. Suppose if I start talking in my mother tongue, I'm pretty sure none of you will understand anything. Why? You don't have a context. You don't even know ABC of it. You don't have any nonsense about it. Why? Because you're in vacuum, right? I can't expect you to, ask you like, okay, start thinking in Telugu. You'll not understand anything. So if you feel, right, oh, itna tough question kaisa karenge? No, you should not think that way. Oh, okay, this is how we should handle these kind of models. So that's how we should practice. People have that misconcept, like, oh, I should get the question on my own in the class. Why are you competing with the teacher? Why are you competing with the teacher? The teacher ka job, if I give you 10 questions in the class and if you got all 10 questions, what does it mean? I'm not teaching you anything. So, yeah. So, how do we handle this? At a distance x, we will choose a small slice. But I'm not saying you should not get it. If you get it, it is awesome. If you don't get it, you should not become like, oh, what? You learn something new. So we took a small slice here. I'll exaggerate the figure. Can you imagine how this piece looks like? Did you ever take a watermelon ka piece? You'll have a watermelon ka piece like this, and after eating, whatever is left out, doesn't it look like that? Right? After eating the red color part, the small piece, what is left, it looks like this. So this thickness is dx, right? And let this area be A, which is a very small area. I'll just call it A. Perfect. Now, on this small piece, what are the forces acting? So we have tension, right? We have EQ, that is the electric field at that point into the charge Q. And here the tension is T plus dt. Perfect. So this is all the stuff we got. So what is the volume of the small piece? The volume will be area into thickness. So the charge of the small piece Q will be the volume charge density into AdX. So this much charge you have on that small piece. And what is the field at that point? I hope everyone remember the field inside a solid sphere. KQ small r by r cube. Remember this? KQ r power 1 by r cube. But question may it is given in terms of rho. So let's write in terms of rho. So K will be 1 by 4 pi epsilon r cube. Cube is nothing but rho into 4 by 3 pi r cube into small r. If you do this, you actually get a pretty good answer. Rho by 3 epsilon r. It's a linear function. That's your field. Perfect. I think then I got everything here. So this would be EQ plus T plus dt is equal to T. So we get dt is equal to minus EQ. Right? So that's your change in tension there. And then what is dP then? So dP, that's your change in pressure, is nothing but dt by area. So because of that small change in tension, that will generate a small change in pressure. So that tension by area will give you the change in pressure. So dP, I will get minus EQ by area. The reason I'm getting minus n is because it's telling you indirectly, boss, as you go out, the pressure is actually decreasing. So here the field will be rho r by rho x actually. Because we're taking distance x, let's take it as x. Rho x by 3 epsilon. Yeah, and q is rho a dx by area. So we get dp is equal to minus rho square, a gets cancelled, x dx by 3 epsilon. Please have a look at it here. So what we said, we took a small piece and we said because of the field inside, the small piece is getting pushed outside. Now, because it is getting pushed outside, there will be a tension on the front and the back. Think of like this. If you're standing in a queue, right, and the queue is moving or something, aren't you pushing the guy in front of you and the guy at the back behind you pushing? So if I ask you to draw your FBD, there'll be two tensions, isn't it? The guy in the front, the guy in the back, both are pushing you. So let the tensions be T and T plus dt. Any doubts on this page, you should ask me. Like, this is the main thing. After this, it's over. It's all about choosing an element and figuring out the forces. Clear with this? Any doubts on how did I choose the element? Why did I take like this? Perfect. Then next thing, I had to be careful. Limits ka, I had to be a little careful. So when you take this guy, now this is one mistake people do, the pressure part. The pressure on the open end is zero. So free ends have zero pressure. Right? So remember, the free ends or the open surfaces will have zero tension. You cannot have tension. The simple logic. If you have a tension there, whom are you pulling exactly? So this is the argument I will do. If you say there is a tension T here, I will say, okay, assume a free body diagram considering the outer part. So on the outer part, there is a tension T. The outer part is massless, m is equal to 0. So T is equal to m into A, m is 0, therefore tension is 0. You can't push vacuum. If there is nothing there, you can't push. There is nothing. So free ends have zero tension. So that's an important idea there. So now when you integrate the limits, this will go from 0 to P. This will be minus rho square by 3 epsilon x dx. Limits will go from R to X. The pressure is 0 when X is equal to R. So P is equal to 0 when x is equal to r. So this will give you P is equal to rho square by 6 epsilon x square minus r square. You can push it inside and you end up with rho square by 6 epsilon r square minus x square. That's your pressure, everyone. And if you put x is equal to 0, you'll get the pressure at the center, and that is a maximum pressure. The guy at the center actually experiences maximum pressure even though the net force is 0. So I'll put on the result. I'll give you a little more context. So the pressure will be rho square by 6 epsilon into r square minus x square. And at x is equal to 0, the pressure will be rho square r square by 6 epsilon. This would be the maximum pressure. Now, like what Arya was saying, center mein, why is the pressure not 0? I'll tell you what is happening. Listen carefully. Think of it like this, okay? We have a molecule here. 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 Right? They're joined by some bonds. Now, this is how you should think. This guy is getting repelled outside with a force F1. This guy is getting repelled with a force F2. This guy is getting repelled with force F3. This guy is getting repelled with F4. Now, if I ask you what is the force acting on this thing, isn't the sum of all these forces? And similarly, there is one molecule on this side also. This is also pulling with F1. This is also pulling with F2. This is also pulling with F3. Even though the net force is 0, what will be the tension on that middle molecule? Won't it be equal to that? Meaning if I take a block and if I apply F is equal to 100 and F is equal to 100, what is the tension in the block? 100. I hope you're getting the difference, right? Net force is 0, but tension 0 nahi hai. So don't get confused between net force and tension. They're not the same. This is what is happening. Every molecule is trying to fly away, but the inside molecules are pulling you inside. So that puts a pressure there. Any doubts on this? All clear with this? So we got the pressure. Question abhi tak hua nahi. Now the next part of the question, find the force on one half due to the other half. How do you approach that? I know the pressure. So listen, since you know the pressure, let's take half of the hemisphere. That's what you want to find. You want to find force on one half due to the other half. And now I know the pressure inside this thing. So pressure is rho square by 6 epsilon r square minus x square. And this is what we can do. Consider a thin ring here at a distance x and thickness dx. So on the thin ring, what is the force? The force on the thin ring, so that is the surface there, is the pressure into the area, which is 2 pi x dx. So this would be rho square by 6 epsilon r square minus x square 2 pi x dx. This is the force acting on the thin ring due to the pressure which is developed inside. Now, if you take the force on that entire, if you just do the summation of all this, you'll get the force on the hemisphere, which is integral rho square by 6 epsilon 2 pi r square minus x square x dx. And this will go from 0 to r. Because if I know the pressure on that surface, I can take a section and I can integrate and finish it off. Integrate this, you end up with rho square pi by 3 epsilon, that would be r square x square by 2 minus x power 4 by 4. Limits will go from 0 to r. That would be rho square pi r power 4 by 12 epsilon. That's the force. That's a pretty good result. That's how you can do with the pressure. Clear with this? Any doubts on this thing? You can do this even better. Even without finding pressure, you can do this. So listen to this thing. This is the good one. Listen to the idea here. This is what you're going to do. So when you take the full sphere, right? Uh, take a small piece here, dq. Now, due to the small sphere, at this point here, you will have a field here, E, which is rho by 3 epsilon r bar, isn't it? That's the formula we derived. So, which is rho r by 3 epsilon. Na? This was the field. So I can write rho r bar by 3 epsilon. It's a field which is radially going away. Perfect. So if someone asks you to find the force on the hemisphere, all I need to do is the summation of all these forces in vector ways. So that will be integral E dq. That will give you the vector there. And this would be rho by 3 epsilon r dq. So this is a rho by 3 epsilon is constant, integral r dq. Now we have seen this somewhere. Think of this. Integral r bar dm by integral dm. This is nothing but r com. Remember this? Integral r dm by dm is center of mass. Now, if you look at this, can I just replace this with r bar dq by integral dq? And this will still look like r com. We can also call this thing a center of charge, which we have done before in that hemisphere question, if you remember. That means Max cannot tell the difference whether it is R or M or Q. It looks the same. That means from here we can say this is integral R dq is nothing but the total charge Q into the R center of mass. So using this logic, I can replace this whole thing with rho by 3 epsilon, right? And we can write this thing is the Q of the body, whichever body you are taking, and R com of the body which you are choosing. The only reason it works is because the field is R power 1. Once you go outside the sphere, you can't use this because outside the sphere, the field is 1 by R square. Are you clear with this? This is very specific. It is working because it's R power 1. So this is your formula there. So the force on a body is simply rho by 3 epsilon, the charge on the body into R com of the body. So let me show you how this works for our question now. So what are you trying to find here? You're trying to find the force on the hemisphere. So for a hemisphere, anyone remember the center of mass for hemisphere? This is a solid hemisphere. Anyone remember the center of mass? Near area, right? Utsa 3r by 8. So what is the Q of the body here? Q of the body is rho. It is half of the volume, 2 by 3 pi r cube, because you're taking only half of it. So force on the hemisphere will be rho by 3 epsilon. Remember the formula? Q of the body and r com of the body. Rho by 3 epsilon, rho 2 by 3 pi r cube. The center mass of the body is 3r by 8. 3 will cancel, 2 will cancel, we'll get 4, we'll get rho square. r power 4 by 12 epsilon. Rho square pi, I forgot a pi somewhere. Yeah, rho square pi r power 4 by 12 epsilon. Rho square pi r power 4 by 12 epsilon. Same answer. Did you see how we played around everything? We said electrostatic pressure, then we said, and then we got center of mass also came into the picture. So we have electrostatics, we have center of mass, yeah, pressure, we have everything. That's what makes this question really good. So this second technique, right, is pretty useful if you just want to find the force on the hemisphere and you don't want to find the pressure inside. So you can get this answer without using pressure. All clear with this? The advantage of the second method, right? I don't care what is the pressure inside. Without pressure, I can do this. But if I have to do with pressure, problem becomes two levels. The first level is to find the pressure. That itself is a very complex question. And then finding the thing. So it becomes a two-layer question. So if it's an advanced paragraph, they would ask you pressure in this. But if it's a single choice question and they ask you find the force directly, then you're dead anyway. But this is how you do it. Today's class is heavy. Getting it? You are supposed to feel it little tough and yo, this is going little on the boundary. And if you're feeling that way, good. All you need to do is go home tomorrow. Tomorrow you have to just sit and revise the whole thing again. Right? You can see these questions here. The solid sphere, pressures. These are not straightforward questions. You won't put one formula and get an answer. You need to think. Manageable. I'm sure you're understanding though. So this is the pressure derivations. Once you get dp from here, integrate. All clear with this? Great. So take a break. Come back by 9:40. We'll continue from here. Chalo, let's start off. Camps on everyone. So I'll give you a homework question. Give it a try. You guys are exhausted. If I do this also, you'll go mad. So give it a try. So when we meet up next class, we will discuss this thing first thing in the class. So what if I have two hemispheres like this? So that is one half and this is one half. And they have a common center. This is Q1, R1, and this is Q2 and R2. So two hemispheres, different charge, different radius, right? That half and this is half. And they have a common center. These are hollow hemispherical shells with common center. Both are positive. Find the force between them. Since both are positive, they repel each other. Give it a try. Spend some time. Think about this. It's a good question. You should spend time on this and this solid sphere ka pressure and this hollow sphere ka pressure. So these are really good ones. These three, right, are really good stuff. You need to definitely check it out. Clear with this? That's one thing about the sphere and down. Again, whatever you're learning here, everything will repeat exactly the same way in gravitation. If you guys are not planning to keep your cams on, no props. You can leave the class. You can come later when you are ready to switch on your cams. I'll just remove you and block you. I'll put you in a waiting room. I think that will be good. You guys can wait in the room and relax. Hope you all are planning to give JE next year, right? Or in 2020, 30 or 2099 or something like that. No, right? So, next thing. relation between field and potential. So we have studied about field and potential, so we can relate them. This is again a good concept, decent one. Exact same thing you'll have it in gravitation. The symbols also won't change, so we are going to skip this completely in gravitation. So whatever you learn here, it'll be exactly same there. We will wrap up this chapter by Thursday. It might spill over a bit, but next week we'll wrap it up. Next week we'll start off with gravitation. That's what I'm telling you. Please start solving electrostatics. It's almost we are pretty close to finishing it off. You need to start working because if your electrostatics is good, your gravitation becomes really easy. And gravitation will go fast. We'll wrap up that also in mostly 3 classes. So dW is equal to minus du. You studied this in work power energy. Work done by internal conservative forces. This is negative of change in potential energy. So what is work done? F bar dot dr bar. That's your work done. What is potential energy? Charge into potential difference. Remember that? Potential energy is charge into potential difference. But what is force? Force is charge into field. This is minus q dv. So we get E bar dot dr bar is equal to minus dv. Now you can write this in two forms. You can integrate this. We'll get VA minus VB will be minus integral E bar dot dr. So limits will go from A to B. A is the final, B is the initial. This is called integral form. If someone gives you electric field and they ask you to find potential, we use this. You can also write E is equal to minus dV by dr, which can be written as minus dou V by dou xi cap. Do you guys remember this partial differentiation? We have seen this in work power energy. Minus dou V by dou y j cap minus dou V by dou z k cap. If you remember this was a thing there. Force is equal to minus dou u by dou xi cap minus dou u by dou y j cap and dou u by dou z k cap. This is your differential form. When to use this? If someone gives you potential and they ask you to find field. So these are the two forms. So if I give you field, I can find the potential. If I give you potential, I can find the field. You should note these two things down. You will need this. So this is the differential and the integral form to find this thing. Quite an important thing. And what does the minus sign indicate? The negative sign indicates, this is a very powerful statement. If you go in the direction of the field, potential decreases. Means the more and more you travel along the field, the less and less energy you can extract from the system. In the direction of the field, potential decreases. So there was a question like this in JEE. Yeah? So there are lines like this. So this is point A and this is point B. This was the question. Compare which one is more, the field at A or field at B, which is bigger. Compare the potential at A and potential at B. What do you guys think is the answer? So these are the electric field lines and there are 2 points A and B. Compare the electric field at A and B, compare the potential at A and B. Do you guys remember what is electric field? We wrote this in the properties of field. This one, see, the number of field lines per unit area is proportional to field. So if you have more lines in a smaller area, means field is more. So here you can clearly see at B, there is more concentration compared to A. So B is greater than A. But in the direction of the field, the potential decreases. So field is going from A to B. So A ka potential must be greater than B. Clear with this? That's a pretty good mains level question. This is what I was telling you. Mains may questions will be, meaning you'll find at least 15 questions which are straightforward like this. People go for this and come. I think last time, na, max mein some guy got 8 marks and he got 97.5 percentile in max. 8 marks. The paper was that hard in max. Physics mein people got 80, 82 and they still ended up at 98.5 percentile. But anyway, end of the day, what matters is your total score. So that's mains paper. Advanced paper doesn't look like that. Any doubts on this page? This page is very important. Please note down the thing in the red box. You will need these two. So we derived this. So all clear with this? Great. Let's see a question. This is the homework thing. Let's say the potential is xy square, yz square. Find the field at 1 comma 1 comma 1. Let's get this. I think that might be right, Samyak. Let's see. Param, field is a vector quantity. What are you even finding? Okay, Shreyan, that looks right. Let's see. Let's see. So what is the field? E bar is equal to minus dou V by dou X I cap. So what is dou V by dou X? So I hope you guys remember when you're differentiating with X, everything else is constant. So this will be Y square. So YZ is anyway constant. So dou V by dou Y will be X into 2Y plus Z square. Dou V by dou Z will be Y2Z. Y square I cap. 2XY plus Z square J cap. Minus 2YZ K cap. This is your field in terms of XYZ. Now put 1, 1, 1, 1. Minus I cap, minus 3J cap, minus 2K cap. Have a look at this. Yeah, let's see one more. This is Vx. This is Vy. This is Vz. So you're finding potential between Vx, Vy, and Vz. This is 45 degrees. This is 30 degrees, and this is 60 degrees. Using this information, find the field in the region. In case you don't have about the partial differentiation, you should check out the notes in work power energy. That's the first time where we introduced partial differentiation. What are the catch? Again, ask yourself. So what did I give you indirectly? The slope is dou v by dou x, isn't it? So this is the slope. Dou v by dou x is tan 45, which is 1. Dou v by dou y is minus 1 by root 3. And dou v by dou z is minus root 3. That's it. So indirectly they gave you the slope. So this will be minus dou v by dou x I cap minus dou v by dou y j cap minus dou v by dou z k cap. So substitute here. You end up with minus I cap plus 1 by root 3 j cap plus root 3 k cap. Clear with this? Yeah, right up. Yeah, most of you got it. That's an easy one. Let's see the next one. You can see straightforward questions, huh? Matlab, let's say we have point A 1 comma 1 and we have a point B 2 comma 3. So let's say the field is given by E is equal to xi cap plus yj cap. Let's say the field is given by y square I cap plus 2xy j cap. Find VA minus VB. Now it is an integral form. I'm giving you the field and I'm asking you the potential. You have to use the integral form here. You might be thinking, oh, this thing is looking weird. You have done these questions, If you had revised work per energy, if you will see, we didn't call it field and all, but it was the same stuff. Mm, remember this question? See, I gave you force and I'm asking you find work done. तो फोर्स का प्लेस में फील्ड था, वर्क का प्लेस में पोटेंशियल था. So how do we do? Let's see. 11 by 2, 11 by 2 and 17. 3. How the hell did you get potential in I cap and J cap, God? Potential is a scalar quantity. See, let's see the first one. So VA minus VB is minus integral E bar is xi cap plus yj cap. The dot product. dr bar is what? dxi cap plus dyj cap plus dzk cap. So that is your dr bar. If r bar is your position vector, then this is I cap, j cap, and k cap. So this would be minus x dx. This would be minus y dy. That's straightforward. What are the limits? This will go from, remember, a minus b. So a is final, b is initial. So this is xb, which is 2. You're going till xa, which is 1. This is yb, which is 3. And this is ya, which is 1. This is minus x square by 2. Limits will go from 2 to 1. Minus y square by 2. Limits will go from 3 to 1. Substitute this thing here. You will end up with 1 square 2 minus 2. 1 square minus 3 square by 2. That will be 3 by 2 plus 11 by 2. Check. That's how we do it, everyone. Can you do for the second one? Second one is this y square I cap and 2xy j cap. How will you approach this? So E bar is y square I cap plus 2xy j cap. So using this as a reference, try to solve. I'll give you a minute. Right, Utsa, you got the first one. Right, Shriyansh. Get the second one. Anyone remember how to do this thing? We call these things something. If anyone remember, there's a name for these things. Perfect differentials. So VA minus VB is minus y square I cap plus 2xy j cap dot dx I cap dy j cap and dz k cap. When you do this, you end up with y square dx plus 2xy dy. Now, you cannot integrate this separately, but if you keep it together, you can clearly see this thing is nothing but d of xy square, isn't it? So it's a perfect differential. So d of xy square is y square dx plus x into 2y dy. The first time you heard a name like this was in work power energy, perfect differentials. Perfect differentials are conservative forces. So you're done. So basically we can say put xy square is equal to t. Then ta will be put 1 and 1. tb will be 2 and 3. That's 18. So this guy will become minus integral dt. Limits will go from ta, which is 1, to tb, which is 18. This would be 17. Check. Be careful with the signs. It's final minus initial. Samya got it. Aditi got it. Utsa got it. Yeah, most of you got it. All clear with this? Any doubts on this? Perfect. Let's see one more. We have an infinite line charge. Lambda is your linear density. There's a point A here and there's a point B here. Let this distance be R1 and let this distance be R2. Find VA minus VB. I don't know, Srihari. I don't know. Ask your math teacher if there is any concept like that. So ask your
Sir,
math teacher and see what
sir,
it is.
you said
Partial
that
integration.
that's a perfect differential, sir.
Yeah,
Sir, but can't we partially integrate that? I
that's what
mean,
I'm saying. I don't know any concept like that yet. I didn't learn it anywhere. So talk to your math teacher. Ask him if there is anything called partial integration. If he says yes, then please
sir,
go
so
ahead. I
what is
can't
the
do it.
opposite of partial differential then?
I don't know, Ray. I'm not a math teacher. Why are you asking me?
Sir, if we dou V by dou R is this E, so then what should be V when we get R, sir? Like any vector.
Where is R? What is R
Sir,
you're talking about?
sir, dou V by dou X is E, no? So minus dou V by dou X is E.
Minus dou by dou x is E in x direction. That is not E.
Yes, sir. So, can't we do something like E dou X is dou V and then partially integrate to get V, something like that?
Yeah, you can do, but you can't do for this function. So do it now. If you think you can do it and tell me how you can do it.
But the answer is not coming.
Because you can't do it. Arey God, how will you even integrate y square dx? Why are you removing y square out of the integral? Y is not a constant, y is a variable.
So we cannot do partial integration like that, sir. It's not
Talk to your
good.
maths teacher. Talk to your maths teacher and see what he says. He'll punch you right and left, then come and tell me. You're asking me because I can't punch you. तो मैथ्स टीचर को पूछ के देख क्लास में जाके टीचर मैथ्स टीचर इज देयर टीच मी पार्शियल इंटीग्रेशन बस ये बात तो मैथ्स टीचर को बोलो एंड तेरा मैथ्स टीचर ना इफ ही विल पंच यू राइट एंड लेफ्ट मतलब I have seen this max people, right? Genuine max people, right? They're very authentic people about max. You talk shit in front of them, kick you right and left. Until unless you have invented a new concept like partial integration, right? Which I don't know if it is in existence, right? I'm not that strong in max. हो सकता है, or maybe you have created one, so you can publish a paper. So then, yeah, you will. I think Max के लिए Nobel Prize नहीं है, but there is something equivalent. So you can't do it. At least till now, I have not seen it. So my knowledge is lacking, Srihari. So not your fault. So forgive this innocent physics teacher who is not good at math. So I know only this much integration. So let's do this thing. ऐसा कुछ concept नहीं है. There is no partial integration. Idea तो अच्छा है, but I don't know. I never heard about it. How do we do this thing? This is a straightforward question. ये डाउट ना तुझे वर्क पर आने में, when you see we had the problem there also, देखो it is the same question. You couldn't integrate this. Y dx x dy, because y is a variable you couldn't integrate. एक बार वर्क पर आने चेक कर लेना. We did a question like this. देखो, if you have to integrate, I have to tell you what is the relation between x and y, or else you can't solve. So yeah. So how to do this thing? This is a straightforward. Electric field is equal to 2k lambda by r. Normally we do like this thing in physics. याद है? We say like this thing, dv by dr and dr, and we say dr cancel करके this becomes dv. We do this thing. If you show this to a max, he will punch you. Because if you guys remember, I told you this also. This d by dr is what? It's an operator, isn't it? That whole thing is one term. You cannot cancel dr and dr. That is bullshit actually. Physics में काम चलता है, right? The physics when you put dr and cancel out, it is as good as putting a differential. It works. But if you show that to a math teacher, right, they will punch you. So yeah. So what is this thing? 2k lambda by r and va minus vb. The same story there. 2k lambda by r dr. What are the limits? Always be careful. Huh? I have seen people goofing up these limits. A is your final. So that's the upper limit. B is your initial. That's your lower limit. So this would be R1. This is RA, which is R1, to RB, which is R2. This would be minus 2k lambda. That will be ln R1 by R2. Send the minus inside, you'll get 2k lambda ln R2 by R1. I hope you can see these are straightforward questions. I'll give you the field, you'll find the potential. I'll give you potential, you'll find the field. So easy stuff. Clear with this? These are straightforward mains and bits and CT level questions. These are. The next one. Any doubt so far? Anything you're not clear? Please ask me. Sudiksha, clear with this? Trishi, Utsa, Vanshika, Vedika, clear? Pratyasha, Param, Shreyansh, clear? Sleepy, Shreyan, clear? Let's see one more. Which of the following are possible? So I'll give you 4 options and you have to tell me which of the following are possible. The electric field is 0, potential is 0. Can you create a system where both are 0? Electric field is not 0, but potential is 0. Electric field is 0, but potential is not 0. Electric field is not 0, potential is also not 0. So if it's a more than one choice question, there are 4 options. Which of the following is possible? Meaning you can take any charge, you can take any system, you can take whatever you want with the charges. And is there a way to create these things? First was the easiest one, right? Don't put a charge. E0, V0. So first is possible. Fourth is also possible. Put a charge. E is not 0, V is not 0. So, नहीं ईश्मान, नहीं सम्यक. Hmm. Right. No, Aditi confused. So finally, what is the answer, Aditi? No, Param. Right, हो गया. नहीं, Shaurya. Right, Aditi. All are possible. See, I will modify the question. You can do it even better. Let's say E is 0, dV is 0, E is 0, dV not equal to 0. People get confused between V and dV. Both are not same. They're completely two different things. E is not 0, but dV is 0. E is not 0, dV is also not 0. There are 8 options, right? Now let's try to do this. First one is possible. How? Don't put any charge. This will be right. Second is also possible. How can you get this? Consider a E is not 0, but V is 0. Consider two charges, plus Q and minus Q. At the center, field is not a 0 because they're in the same direction, but potential is 0, isn't it? Because potential is a scalar quantity, kq by r minus kq by r. So B is possible. C is also possible, where you take a hollow shell. The field inside a hollow shell is 0, but the potential is not 0. Field is 0, but the potential is kq by r. E is not 0, V is 0, that is also fine. Now here, this is where you have to be careful. Your relation between field and potential, E is equal to minus dV by dr. Now, this is where people think, sir, if E is 0, V has to be 0. Not necessary. See, I can have a potential V 1, 1, 1, 1. So everywhere it is 1. dV is 0, but the potential is not 0. Isn't it? I can also have a system like this. Minus 1, 0, 1, 2, minus 2. dV is not 0, but V is 0. I hope you're getting the difference. dV and V are completely two different things. So E is minus dV by dr. So if E is 0, dV has to be 0. But V need not be 0. So don't get confused with this. The change must be 0. The V ka value need not be 0. Now, using this idea there, you can clearly see this is right, this is wrong, this is wrong, and this is right. Check. Is this all clear with this? It's a very good theoretical one. This is a question from HCV. The first 4 options, though. So most people get confused with V with the dV. They say that on E0 to V0. Nay, dV0. Both are not same. All clear with this? Yeah, G is not possible. The next thing, equipotential surface. Look at the word, the whole word is self-explanatory. Equipotential surface. So the surface which has equal potential everywhere. Can you explain G? देखो ना रे, oh yeah, यही है. E is not 0. How can dV be 0 then? It just comes from this equation, right? Mathematically. Field is not 0, but dV is 0. See, what is dV 0? Means the potential is same everywhere, right? If the potential is same everywhere, how can you have field in that region? Because in the direction of the field, potential will change.
But if we go perpendicular to the field direction, then T will be 0 because the TV equals to integration of E dot dr.
No, you're again getting confused. When I said dV, I didn't tell you dV in which direction, right? So when I said simply dV, it is a generic, meaning from that point, if you go in any direction, the dV is 0. What you're saying is true. What you're saying is, if I go in a particular direction in that dV, right? So then, yeah, you can say, if let's say this x, then if dV in x is 0, then dEx is 0. So this thing dv, right? This includes all the change in potentials in all directions. Basically, this E will include all that ex, ey, ez. Got it? अगर सोचो मैंने ये बोला होगा, if I said dv by dx is equal to ex, this is a different story. What you're saying is true. So when I say dv by dr, I'm taking the potential in all three x, y, z. So yeah, but what you're saying is true. That's a good one. Equipotential surface, a surface or the region where the potential is same throughout. Now, what are this example? You have seen this already a lot of times. So let's say if you have a point charge, let's say plus q. If you take a shell at a distance r, so the concentric shells, let's say this distance is r1, so this entire shell will have a potential of kq by r1. This is called equipotential. Now, if you take one more shell at a different distance, r2, this entire shell will have a potential kq by r2. That means for a point charge, the concentric shells are equipotential. See, all the shells are not equipotential. Each shell is an equipotential surface. Each shell is an equipotential surface. Each shell has a different potential, but that entire shell has the same potential. Each shell is an equipotential surface. They're just examples. If you take a hollow sphere, the potential inside is kq by r. This is constant. So this is equipotential region. So the whole region has same potential. Yeah, you can take other shapes also. For example, if you take an infinite line charge, so for an infinite line charge, the equipotential surfaces are cylinders, coaxial cylinders. So each cylinder is an equipotential surface. So basically, if you can find a surface where the whole potential is same, it's called an equipotential surface. Can you guys tell me, if I take plus q and minus q, is there an equipotential surface? If you have plus q and minus q, is there an equipotential surface? In the middle. So if you draw a plane in the perpendicular bisector, it's not a point. The whole plane will have zero potential. Perpendicular bisector plane. Because from here to here, if you take any two points that are equidistant, the potential is zero. So the whole plane in the middle of the charges, the perpendicular bisector has a zero potential. Are you clear with this? So any region or the space where the potential is same is called equipotential region. But the same thing also applies for gravitation. So whenever you're launching a satellite or anything into the space, right? Let's say you're sending it to some far off planet. This NASA and all these people, right? They actually try to calculate regions of equipotential. Think about this. Let's say you're sending something from this planet to this planet, and it's very difficult to calculate. But let's say you found out some equipotential region like this. What is the meaning of that? Meaning, if you can take a rocket and send it to the equipotential surface, now because the potential is same everywhere, you need not do any additional work. You can make that satellite travel along this line, right? And when you get to the closest point, you can take a detour there and you can travel from here. You can save all the fuel while traveling from here to here. So if you can find regions like that in the space, you can actually use that to navigate. It saves you a lot of fuel. We don't have equipotential regions, but airlines do something like this. You should try to look at a flight, from Mumbai to Japan, Tokyo. When you go from Mumbai to Tokyo, I think it is 8 hours or 9 hours direct flight. But while coming, I think it is 10.5 hours ka flight. Direct flight. There is no stopping in the middle, nothing. It could be a little more extra time, because Mumbai ka airport landing and all is a mess. Maybe there's a delay and all, but you almost get a difference of 45 minutes to 1 hour. There are something called, streamlines, not streamlines. There's a name for that.
Jet streams.
Jet streams. That is the word. If you heard this thing, there are called jet streams. So these are, it's like the way we have water, water flowing on air. These are the air, flowing in the right, Srihari, in the atmosphere. These are called jet streams. So these are the winds blowing, and these have good speed, 70, 80 kilometers per hour ka speeds they blow in the atmosphere. So if you can take your aeroplane and go along the jet stream, you get that additional speed. You can save the fuel. So there are companies which actually track these jet streams and sell that data to aeroplane companies. So, and this has to be updated every day, right? It's a good business model. It's difficult to track them, but if you can track them and if you can keep on selling this data every day, and just think about it, if you can add a speed of additional 80 kilometers per hour, even 50 kilometers per hour for an aeroplane, you're saving a lot of fuel, and fuel is expensive. And it is not one single plane, isn't it? It's like a highway there. So, abhi problem वही होता है. While you're coming in the reverse, you have to cross the jet stream and come. So it takes more time. So one way you can save fuel, the other way there is no way out. So if you check like that, you will see flights sometimes, right, to and fro, it doesn't take the same time. There's a difference. Yeah, but yeah, Mumbai ka airport, right? Indian domestic airlines are different. The flight only takes 1.5 hours, but they will say 2.5 hours just to keep you happy. Because they'll say 2.5 hours, they will land the flight in 1:45 and say, Dekho, we have arrived early before you. So be happy, and you get so excited. And you go there to the luggage counter, and the luggage does not come for another 45 minutes. The end of the day, it is useless. You must have noticed that it doesn't matter. Like, first of all, the airplane is just flying around the airport. When it lands, it takes 20 minutes to get out. When you go for the luggage, there you are waiting anyway for 45 minutes. And people are there standing in the queue and fighting each other. I'll get down first. So, like, what's the point? Yeah, until unless you need to go to the washroom, I don't see any point in getting down the plane and running on that thing. So, anyway, so it goes like that. So, let's write down the properties here. Next class, we'll see more problems on this. So, what are the properties of equipotential surface? The first thing, the work done in moving a charge on equipotential surface is 0. Why? There's no potential difference, and charge into potential difference is work done. So you can travel on the potential, equipotential surface without using any energy. If you give a velocity v, it will maintain that speed. It will maintain that constant velocity. The electric field lines are always perpendicular to the equipotential surface. This is one really important property. Are always perpendicular. Why are they perpendicular? Think of like this. Let's say this is your equipotential surface. And let the field be at an angle. And I can resolve this into two components. So let the field be here, which is E cos theta. That's your tangential field. There'll be a perpendicular component E sine theta, which is your radial field, or the E perpendicular. Now, you guys remember the statement we wrote? If you travel in the direction of the field, the potential decreases. So, because of that E tangential, the potential should change. But potential cannot change because you said it is an equipotential surface. So, in the direction of E cos theta, potential decreases. So, if you have field along that surface, you have to change the potential. But you're telling me it's an equipotential surface. Since it is equipotential, E cos theta has to be 0. This is not possible. Therefore, E cos theta must be 0. Theta must be 90. So that's how you can prove it by contradiction. You'll say if there is a field along the tangent, then the potential will change. And if the potential changes, then it's not equipotential anymore. So just to give an example, look at the shapes. When you took the point charge plus Q, how are the field lines? The field lines are going away from the charge. This is how they're looking. And how are the equipotential surfaces? They are shells. This is equipotential. And you can clearly see here, this is 90, this is 90, this is 90, 90, 90, 90. Perpendicular. If you guys remember this, plus Q and minus Q. We said the central plane is equipotential. If you actually try to draw the field lines, the field lines actually converge here. So you can clearly see these field lines are actually perpendicular. So they will be always perpendicular. Third, the equipotential surfaces cannot cross each other. Why? If they cross each other, just now you made a statement, the field has to be perpendicular. So the field has to be perpendicular to this, and the field also has to be perpendicular to this guy. You get two possible directions of field, not possible. Right? So let me show you something. Hmm, just give me a minute. There is something I saw last time. I'll send you this link also. You can check. Where is this? Yeah. Okay, see this thing. So this is how you can actually draw the field lines here. Can I make this smaller? Okay, so look at this thing. So you have a full screen here. You can literally put a lot of charges here and you can do a lot of simulations here. I can make the grid something like this. So you can put a positive charge. So the red means negative charge. The blue is the positive charge. Then you can put two charges like this. And on the left hand side, you can see there's a start and stop. If you start, you can look at the field line, see how they go. Can you see how the field lines look? And you can add more charges if you restart clear. Let's put more charges. I can put a plus. I can put a plus. I can put a plus. That is plus. I'm making a hexagon kind of thing. So that is one and that is one. So there are 6 charges. And now if you start. Nice, no? You can play around. I can put one negative charge now. I can put one negative. I can put one negative. And if you start, the whole lines will. So there, if someone is entering a Rangoli competition, you can use this. So put some charges, start, look at field lines, and you can use this, to figure out this stuff. It's a pretty nice stuff, and you can change the magnitude. You can do a lot of stuff. I'll send you this thing. Okay, make sure to go through this. I liked it. It is good to see simulation. How are the field lines going, how they look, and everything. So the one which I showed you, right, the plus and minus. If you think about it, so if I put a dot, and if I put a negative, and I'll just make the grid smaller so that we can see. You can make it big or small or however you want. So I'm just putting more closed. I think both become plus plus, so they're just getting repelled. So there you got the idea. So I'll send you that. So make sure to go through that. That's a pretty good one for drawing the field lines. So okay. So that's about the equipotential surface. So next class, when we catch up, we'll continue from here. We will do problems on this, and then we'll do something called dipole. And make sure to try the homework problem and definitely check out the pressure ka questions. So mostly on Thursday, we should be able to wrap up the chapter, right? You can start solving your material. Other than dipoles, you can handle everything. So don't delay. At least finish off whatever you can, like 50-60%. Try to finish off by next Tuesday, because mostly next Tuesday we'll start off with gravitation.